Hi, in this video we're going to look at manometer. Manometer it's often used to measure the pressure of your system, and it is normally constructed with one or more uh, fluids, for example, mercury, water, or alcohol, or oil. So here, let's look at this one. Um, you have a beaker that is open to air, so where this point is right here, if we call this point point 2, and that point 2 is going to have a pressure of atmospheric pressure because it's taking out, it's where in contact with atmospheric pressure, so it's going to be taking up the atmospheric pressure. Then you have the top fluid layer 1, and so if we were trying to figure out point 3 here, what's the pressure at 3, P3? Because what is that equal to? Because we already know earlier P2 is going to be atmospheric pressure. How about 3? 3 is going to be deeper. You know, we learned about the pressure increases with the depth. And so it's P atmospheric pressure, originally from P2. How much increase? Rho, the equated 1 density, G, height, it's the difference between 2 and 3 is H1 because it increases H1, so rho 1 G H1. Now we continue going down deeper at point 4 here. So at point 4, we know it's going to be even higher pressure than point 3 because it's deeper. And we're going to just copy down the pressure at 3. Then we know it's more. How much more? It's going to be rho. The fluid right now is liquid too, rho G. And the difference between 3 and 4 in terms of depth is H2. So that's how much more pressure at 4 compared to 3. And then at the bottom, which they already label as 1, so P1 here, it's going to be even more pressure than P4. So let's just copy down the P4 here. And how much more? It's liquid fluid 3, so it's going to be density 3 times G, and the depth is H3 for this fluid. So that's telling us the entire pressure, the pressure at the bottom, 1, which is right here, right? So in a stack up fluid layer, the pressure changes across the fluid layer of density, and the height is rho GH. That's the difference between them. Now let's look at this manometer. You have a gas and you have this fluid in here. And so if you want to go ahead and draw a dashed line between 1 and 2, and you notice 1 and 2, they're at the same height. We talk about if it's at the same height and it's in the same fluid, they are going to have the same pressure, right? So P2 is going to be equal to P1 here for this problem. P1 is equal to P2. And if you were trying to figure out what is the pressure inside this, what's the pressure of this gas? Well, remember the gas, if it's in the room or in a container, the pressure does not change much, right? The change is negligible. So if the pressure here will be similar to here or here or here, point 1, because at point 1, that's going to still take up the pressure you're solving. So in other words, if you want to know the pressure here of the gas, it's going to be the same, equal to P1. So if you, and also you know P1 is equal to P2, right? If you know P2, then you find the P1, since that equal, and then you find out your gas pressure here. So how do we figure out the pressure 2? Then we use the old concept, because right here it's the open beaker and here it's connected to atmospheric pressure. So at this point it's P atmospheric pressure. And then 2 is what? Below, it's increased the depth, so the pressure will be higher. Like we talked about, when you go scuba diving, you're going to have more pressure. And how much more? It's going to be rho GH. So from atmosphere pressure plus rho GH to get your P2, and P2 is going to be equal to P1, and P1 happen to be your gas pressure. So that's a simple manometer problem. All right, so now let's look at a manometer that might have multi-fluid. Then how do we figure out the pressure? For this instance, you have air, and you want to find out the pressure of air here. We do not know. That's what we want to measure. So the first fluid contact, it's water. So air and water contact, and then you have second layer of liquid, that's your oil, and then you'll have another one, it's mercury right here. So they have three different fluid. So the way to work on this type of problem, we know we're just going to do one at a time, one band at a time, or one liquid at a time. So let's see, we have to start with something we know. Among all those points, do we know somewhere the pressure? Do we know the pressure at some point? Yes, we do, because P2, we know. P2 is open to the air, so it's taking up atmosphere pressure. So we start with P2, then we're just going through the bands and figure out the next. So if we know P2, now we're just going to find out our point 3 here, right? So that's going to be our first band. So we're going through mercury. That's our mercury. One fluid at a time. So we're looking at here. We know P2, and we just need to figure out P3. The way to figure it out is to look at their height difference. First of all, is 3 lower or higher than 2 in terms of height? P3 is located lower than 2. Since it's lower, it's deeper, it's going to have higher pressure. So in that situation, you know P3 is going to be P2 plus it's going to be higher pressure. How much higher? It's going to be rho Hg, that's mercury, because we're in mercury layer, rho G. The difference between 2 and 3 is this value, H3. So now you figure out the pressure at point 3 from the mercury layer. And then we're going to go to the second layer, which is this layer right here, and our oil layer. And now let's think about oil layer, which is our second band, oil from 3 to 4, 4 to 3. So we know we need to find a P4. However, do we know P3? Yes, we do. So it's P3. We start with P3. Now we're going to ask us the same question. Is 4, at point 4, is 4 located higher or lower compared to 3 in terms of their depth? 4 is above 3. So in that situation, the pressure at 4 is going to be lower than 3. So because of that, it's lower. And here you're going to take up the negative. You're going to minus. How much lower pressure? It's going to be this fluid layer, which is oil, G. And the height difference between 3 and 4 is going to be H2. Right? So now, so far, you started at 2, which is atmosphere pressure. Then you figured out the pressure at 3. It's going to be higher pressure than 2 since it's deeper. And then from this point, you're going to figure it out. You're going to figure out at point 4, since 4 is located higher, so it's going to be lower pressure compared to 3. So the last thing is the very last fluid layer, which is our water layer. So you know P4 now, and now you just need to figure out 1, right? Because it's 4 to 1, they have the same liquid, which is water. So P1, that's our goal to find out. So 1 is located higher than 4. If it's located higher than 4, it's going to have lower pressure. So in that situation, it's going to be P4 minus. And how much lower? We are looking at water layer now. So H2 and G and H1. H1 is the difference between 4 and 1. So knowing that, you can find your pressure at 1. And again, the last connection we need to make is 1 is basically the interface between water and this air we are measuring. So P1 is going to be, you calculate it, it's going to be the air you are trying to solve. Okay? So knowing that, if we're going to combine all of those together, trying to find this P air, which is P1, and we can plug all those in here because you can bring P3, that's your P3, back in here. And all those is P4, so bring all those together to P4. And then you find your P1, which is your air. So in other words, P1 or air is going to be all those, let's write it down, P2 plus, before we do P2, and we already figured out P2 is atmosphere pressure, so I can even replace this P2 with atmosphere pressure. Then we go ahead to have the answer for this. It's going to be P atmosphere pressure, which is 14.696 psi, right? That's 1 atmosphere pressure. So 1 atmosphere pressure plus rho mercury G H3, then minus, because that's your P3, substitute P3, and then you minus oil G H2. Then what you got here is your P4. Then P4 is plugged in here, then minus rho water G H1. Then that's your P1, which happens to be the air pressure you are calculating. So that's the whole thing. Using this manometer to figure out the pressure here. The key is one fluid at a time. Also, determine the height difference within that one fluid. And if unknown you are solving is located deeper, so the pressure will be higher. So you're going to plus rho GH. And if the unknown point is located higher point in terms of depth, so the pressure will be lower, so it's going to be minus rho GH. So that's all boiled down to for this manometer. All right, and the very last thing I wanted talking about is the unit, because if often our pressure at atmosphere pressure, if we were using Pascal, so we know it's 11325 Pascal. Now, if I'm going to find some other pressure, for example, is atmosphere pressure plus rho water G H1. Okay, this is just a hypothetical question. I want to work on the unit here, because if we're going to use atmosphere pressure, which is here is in Pascal, which is good, 11325 Pascal. Now, if we're going to use rho, if we are using meter, mass, which is kilogram per meter cube. If it's water density is going to be 1,000, right? 1,000 kilogram per meter cube. Then times G, it's 9.8 meter per second square. And then height, let's see, for example, height here is 10 meter. So times 10 meter. Then I think we have talked about earlier, this rho GH, if you use the standard unit on all of those three terms, you're going to get the unit of Pascal. So you will be able to get the same unit in Pascal. Okay. So just watch out, verify the unit. And okay, I'll see you at the next video. Bye.